Introduction. Arun, how much you scored in science last year?
Teacher, 72.
And how much in maths?
Teacher, 84.
72 in science and 84 in maths. Okay. Shraddha, now you tell me, how much did you score in science and maths?
Teacher, I scored 86 in science and 85 in maths.
Okay. 86 in science and 85 in maths. Pratik, you tell me now. Teacher, 67 in science and 72 in maths. All right. Can you see? I have written your marks in this bracket. What does this represent? Anyone? This represents matrix. Today, we will learn what matrices are and its operations. Come, let's start. Objectives. At the end of this lesson, you will be able to define matrix, explain order of matrices, write different types of matrices, define zero matrix, understand equality of matrices, understand addition of matrices. Definition of matrix. A matrix is a way to organize data in columns and rows. A matrix is written inside brackets. Each item in a matrix is called an entry. Look at this matrix. It has 2 rows and 3 columns. The entries of the matrix below are 2, -5, 10, -4, 19, 4. Order of the matrix. The order of a matrix refers to the number of rows and columns of a given matrix. By convention, the order of a matrix is given by number of rows by number of columns. Here we can see 2 pictures of the same matrix with the rows and columns highlighted. The order of this matrix is 2 by 3, that is 2 rows by 3 columns. Matrix notation. In order to identify an entry in a matrix, we simply write a subscript of the respective entry's row followed by the column. In matrix A, we write A23 to denote the entry in the second row and the third column. A23 indicates the row number 2 and the column number 3. Column and row matrices. Column matrix. A matrix which has only one column is called a column matrix. Example of column matrix. A is equal to column wise 21, 17, 9. This matrix has 3 rows but only one column, so it is a column matrix. Its order is 3 by 1. Row matrix. A matrix is said to be a row matrix if it has only one row. For example, row-wise 3, 5, 1 is a row matrix as it has only one row. Square matrix and diagonal matrix. Square matrix. An m by n matrix A is said to be a square matrix if m is equal to n, that is, number of rows is equal to number of columns. For example, A is a square matrix of order 3 by 3. Diagonal matrix. In a diagonal matrix, all the elements above and below the diagonal are zeros. For example, B is a diagonal matrix. Scalar and identity matrix. Scalar matrix. A diagonal matrix in which all the diagonal elements are equal is called scalar matrix. Look at this matrix. It is the diagonal matrix with the diagonal elements same, that is 7. Therefore, it is a scalar matrix. Identity matrix. A square matrix in which all the main diagonal elements are ones and all the remaining elements are zeros is called an identity matrix. Identity matrix is also called as unit matrix or elementary matrix. Identity matrix is denoted with the letter n by n, where n by n represents the order of the matrix. Zero matrix. A zero matrix or null matrix is one which has all its elements 0. Here is a 3 by 3 zero matrix. These are 3 more examples of zero matrix. The zero matrix is denoted by 0. Equality of matrices. Two matrices are equal if they have the same order and the corresponding elements are identical. In other words, say that an by m is equal to aij and that bp by q is equal to bij, then a is equal to b if and only if n is equal to p, m is equal to q and ai, j is equal to bij for all I and j in range. Matrices P and Q are equal. Here are two matrices which are not equal even though they have the same elements. Example of equal matrices. Given that the following matrices are equal, find values of x, y and z. For two equal matrices, they must have the same size and shape and they must have the same values in the same spots. Or we can say A11 must be equal to B11, A12 must be equal to B12 and so forth. Therefore, by equating the corresponding elements, we can solve for the variables x plus 3 is equal to 6, x is equal to 3, y is equal to minus 1, z minus 3 is equal to 4, z is equal to 7. Addition of matrices. Matrix addition is the operation of adding two matrices by adding the corresponding entries together. Two matrices may be added only if they are of the same order, that is, they must have the same number of rows and columns. Let's add these matrices. We need to add the pairs of entries and then simplify for the final answer. Row-wise, first row 0, 1, 2. Second row 9, 8, 7. Plus row-wise, first row 6, 5, 4. Second row 3, 4, 5. Row-wise, first row 0 plus 6, 1 plus 5, 2 plus 4. Second row 9 plus 3, 8 plus 4, 7 plus 5 is equal to row-wise, first row 6, 6, 6, second row 12, 12, 12. So the answer is row-wise, first row 6, 6, 6, second row 12, 12, 12. Did you know? If A and B are not of the same order, then A plus B is not defined. For example, if A is equal to row-wise, first row 2, 3, second row 1, 0, B is equal to row-wise, first row 1, 2, 3, second row 1, 0, 1, then A plus B is not defined. Addition of matrices is an example of binary operation on the set of matrices of the same order. Summary. Let us summarize what we have learnt. A matrix is an ordered rectangular array of numbers or functions. A matrix having m rows and n columns is called a matrix of order m by n. Aij by 1 is a column matrix. Aij 1 by n is a row matrix. An m by n matrix is a square matrix if m is equal to n. A is equal to Aij m by m is a diagonal matrix if Aij is equal to 0 when I is not equal to j. A is equal to Aij n by n is a scalar matrix if Aij is equal to 0 when I is not equal to j, Aij is equal to k, where k is some constant when I is equal to j. A is equal to Aij n by n is an identity matrix. If Aij is equal to 1 when I is equal to j, Aij is equal to 0 when I is not equal to j, a zero matrix has all its elements as 0. A is equal to Aij is equal to Bij is equal to Bif. A and B are of the same order and Aij is equal to Bij for all possible values of I and j. Introduction.
Where do we apply the concept of matrices?
Matrices is used to obtain compact and simple methods of solving system of linear equations.
Can we use matrices for various computer applications?
Matrix notation and operations are used in electronic spreadsheet programs for personal computer, which in turn is used in different areas of business and science like budgeting, sales projection, cost estimation, analyzing the result of an experiment, etc.
Can matrices be multiplied?
Yes, we can multiply matrices. It has got a different method. Are you interested to learn?
Yes, teacher.
Okay. Today, I will teach you about the multiplication of matrices. Objectives. At the end of this lesson, you will be able to multiply a matrix by a scalar, explain properties of matrix addition, learn properties of scalar multiplication, learn the method of multiplication of matrices, explain the properties of matrix multiplication. Multiplication of a matrix by a scalar. There are two types of multiplication for matrices: scalar multiplication and matrix multiplication. Scalar multiplication is easy. We just take a regular number called a scalar and multiply it on every entry in the matrix. For the given matrix A, find 2A. To do the first scalar multiplication to find 2A, we just multiply a 2 on every entry in the matrix. 2A is equal to 2 into matrix row wise, first row 1, 2, second row 3, 4 is equal to matrix row wise, first row 2 into 1, 2 into 2, second row 2 into 3, 2 into 4 is equal to matrix row wise, first row 2, 4, second row 6, 8. So the answer is 2A is equal to matrix row wise, first row 2, 4, second row 6, 8. Negative of a matrix. The negative of a matrix is denoted by minus A. We define minus A is equal to minus 1 into A. Properties of matrix addition. The basic properties of addition for real numbers also hold true for matrices. Let A, B and C be m by n matrices, then A plus B is equal to B plus A, which is commutative property. Associative property, A plus B plus C is equal to A plus B plus C. Additive identity. There is a unique m by n matrix O such that A plus O is equal to A. Addition inverse. For any m by n matrix A, there is an m by n matrix B called minus A such that A plus B is equal to 0. Properties of scalar multiplication. All the laws of ordinary algebra hold for the addition and subtraction of matrices and their multiplication by scalars. The first property is, if A and B be two matrices of the same order and if K be a scalar, then K into A plus B is equal to K into A plus K into B. Another property is, if K1 and K2 are two scalars and if A is a matrix, then K1 plus K2 into A is equal to K1 into A plus K2 into A, and K1 into K2A is equal to K2 into K1A. Multiplication of matrices. We can multiply two matrices if and only if the number of columns in the first matrix equals the number of rows in the second matrix. Otherwise, the product of two matrices is undefined. The order of the product of matrices is rows of first matrix upon columns of the second matrix. Method of matrix multiplication. Let's now learn the method to multiply two matrices. Let's take a general 2 by 3 matrix multiplied by a 3 by 2 matrix. The answer will be a 2 by 2 matrix. We multiply and add the elements step by step. We work across the first row of the first matrix, multiplying down the first column of the second matrix element by element. We add the resulting products. Our answer goes in position A, 1, 1, that is top left of the answer matrix. We do a similar process for the first row of the first matrix and the second column of the second matrix. The result is placed in position A, 1, 2. Now for the second row of the first matrix and the first column of the second matrix, the result is placed in position A, 2, 1. Finally, we do the second row of the first matrix and the second column of the second matrix. The result is placed in the position A, 2, 2. So, the result of multiplying our two matrices is the multiplication of matrix row-wise first row A, B, C, second row D, E, F, and matrix row-wise first row U, V, second row W, X, third row Y, Z produces matrix row-wise first row AU plus BW plus CY, AV plus BX plus CZ, second row DU plus EW plus FY, DV plus EX plus FZ. Example. Given the two matrices, determine which matrix product AB or BA is defined and evaluate it. Since A is 2 by 3 and B is 3 by 4, the product AB in that order is defined and the size of the product matrix AB will be 2 by 4. The product BA is not defined since the first factor B has 4 columns but the second factor A has only 2 rows. The number of columns of the first matrix must match the number of rows of the second matrix in order for their product to be defined. Solution. Taking the dot product of row 1 in A and column 1 in B gives the 1, 1 entry in AB. The 1, 1 entry in AB is 1. The dot product of row 1 in A and column 2 in B gives 1, 2 entry in AB. And the dot product of row 1 in A and column 3 in B gives 1, 3 entry in AB. The first row of the product is completed by taking the dot product of row 1 in A and column 4 in B, which gives the 1, 4 entry in AB. Now for the second row of AB, the dot product of row 2 in A and column 1 in B gives 2, 1 entry in AB. and the dot product of row 2 in A and column 2 in B gives 2, 2 entry in AB. Finally, taking the dot product of row 2 in A with columns 3 and 4 in B gives respectively 2, 3 and 2, 4 entries in AB. Therefore, AB can be solved to matrix row-wise first row 1, 3, -2, -2, second row -10, 11, -10, 19. Some points to be considered during matrix multiplication. If AB is defined, then BA need not be defined. Non-commutativity of multiplication of matrices. Even if AB and BA are both defined, it is not necessary that AB is equal to BA. Properties of multiplication of matrices. Matrix multiplication is associative. For example, given three matrices A, B and C, the following identity is always true. AB into C is equal to A into BC. Matrix multiplication is distributive across addition. A into B plus C is equal to A into B plus A into C. The existence of multiplicative identity. For every square matrix A, there exists an identity matrix of same order such that IA is equal to AI is equal to A. Example. Find x and y if x plus y is equal to matrix row-wise first row 7, 0, second row 2, 5 and x minus y is equal to matrix row-wise first row 3, 0, second row 0, 3. Solution. Given x plus y is equal to x minus y, mark it as 1 and 2. Now, add the equations 1 and 2, we get 2x is equal to matrix row-wise first row 10, 0, second row 2, 8. Therefore, x is equal to matrix row-wise first row 5, 0, second row 1, 4. Now, substituting the value of x in x plus y and solving it, we get matrix y is equal to row-wise first row 2, 0, second row 1, 1. Did you know? Matrices are commonly used in algebra to solve long equations. The variables such as x and y are taken away and the resulting numbers are organized into rows and columns to form a square or rectangular grid of numbers. These numbers are then calculated to more easily solve the problem. Summary. Let us summarize what we have learnt. Minus A is equal to minus 1 into A. A minus B is equal to A plus minus 1 into B. A plus B is equal to B plus A. A plus B plus C is equal to A plus B plus C, where A, B and C are of the same order. K into A plus K into B, where A and B are of the same order. K is constant. K plus I into A is equal to K into A plus I into A, where K and I are constant. We can multiply two matrices if and only if the number of columns in the first matrix equals the number of rows in the second matrix. A into BC is equal to AB into C, A into B plus C is equal to A into B plus A into C. A plus B into C is equal to A into C plus B into C. Introduction.
Rocky, why are you writing all these numbers in one bracket?
This is not just a bracket. Did you forget what our math teacher taught us day before?
Oh yeah, matrices. So you are solving any problem?
Yes, I am finding the transpose of this matrix.
Transpose? What is that?
Oh, you were not present in the class yesterday? Teacher taught us to find the transpose of the matrix.
Hey, can you tell how to find the transpose?
Yeah, sure. Come, I will explain you.
Objectives. At the end of this lesson, you will be able to find the transpose of a matrix, explain properties of transpose, define symmetric and skew-symmetric matrix, learn elementary operations on a matrix, find inverse of a matrix by elementary operations. Transpose of a matrix. A matrix which is formed by turning all the rows of a given matrix into columns and vice versa. The transpose of matrix A can be written as, for example, transpose of matrix row-wise, first row 1, 2, 3, second row 4, 5, 6 is matrix row-wise, first row 1, 4, second row 2, 5, third row 3, 6. Properties of transpose of a matrix. Here are some properties of the transpose of a matrix. First, transpose of matrix A is equal to matrix A. Second, transpose of matrix A plus minus B is equal to transpose of matrix A plus minus transpose of matrix B if A and B are m by n. Third, transpose of S into matrix A is equal to S into transpose of matrix A if S is a scalar. Fourth, transpose of matrix AB is equal to transpose of matrix B into transpose of matrix A if A is m by n and B is n by p. Examples of transpose. If A is given, then verify that transpose of matrix A into matrix A is identity matrix. A is given. Therefore, its transpose A dash is matrix row-wise, first row cos alpha minus sin alpha, second row sin alpha cos alpha. Multiplying A transpose and solving, we get A transpose A is equal to identity matrix, hence verified. Symmetric and skew-symmetric matrix. There are two important classes of matrices that can be defined concisely in terms of the transpose operation. Symmetric matrix. A real matrix A is called symmetric if transpose of matrix A is equal to matrix A. A is a general 2 by 2 symmetric matrix. Skew-symmetric matrix. A real matrix A is called skew-symmetric if transpose of matrix A is equal to minus matrix A. Here, A is a general 2 by 2 skew-symmetric matrix. Theorems. For any square matrix A with real number entries, A plus A dash is a symmetric matrix and A minus A dash is a skew-symmetric matrix. Any square matrix can be expressed as the sum of a symmetric and a skew-symmetric matrix. Examples. Show that the given matrix A is a skew-symmetric matrix. We have given A, so A transpose is matrix row-wise first row 0, minus 1, 1, second row 1, 0, minus 1, third row minus 1, 1, 0. We can see that this is equal to minus A. Therefore, A dash is equal to minus A. Hence, A is a skew-symmetric matrix. Elementary operations on matrix. Elementary operations for matrices play a crucial role in finding the inverse or solving linear systems. They may also be used for other calculations. There are 6 elementary operations or transformations on a matrix, 3 of which are due to rows and 3 due to columns. We will only discuss elementary row operations, but you may easily adapt these to columns. Elementary row operations. Interchange two rows, multiply a row with a non-zero number, add a row to another one multiplied by a number. Elementary row operations. Let us go through them one by one. Interchange two rows. Symbolically, the interchange of ith and jth rows is denoted as given below. Multiply a row with a non-zero number. Symbolically, the multiplication of each element of ith row by k, where k is not equal to 0, is denoted as given below. Add a row to another one multiplied by a number. Symbolically, the addition to the elements of ith row, the corresponding elements of jth row multiplied by k, is denoted as given below. When these operations are performed on rows, they are called elementary row operations, and when they are performed on columns, they are called elementary column operations. Invertible matrices. An n by n matrix A is called non-singular or invertible if and only if there exists an n by n matrix B such that AB is equal to BA is equal to IN, where IN is the identity matrix. The matrix B is called the inverse matrix of A. Look at this example. Here A and B are given. We can easily check that AB is equal to BA is equal to identity matrix. Hence A is invertible and B is its inverse. Inverse of matrix by elementary operations. This is a fun way to find the inverse of a matrix. We play around with the rows, adding, multiplying, and swapping them until we make our matrix A into the identity matrix I. And by also doing the changes to an identity matrix, it magically turns into the inverse. The elementary row operations are simple things like adding rows, multiplying, and swapping. Let us go through an example in the next screen. Example. Find the inverse of A. We start with the matrix A and write it down with an identity matrix I next to it. This is called the augmented matrix. Now we do our best to turn A, the matrix on the left, into an identity matrix, and the right-hand side comes along with the right, with every operation being done on it as well. But we can only do the elementary row operations, and we must do it to the whole row. Start with A next to I. In this example, our first step is to add row 2 to row 1. Then divide row 1 by 5. Then take 2 times the first row and subtract it from the second row. Multiply second row by minus 1 by 2. Now swap the second and third row. Last, subtract the third row from the second row. And we are done. Examples. Find x if matrix row-wise first row x minus 5 minus 1 multiplied by matrix row-wise first row 1, 0, 2, second row 0, 2, 1, third row 2, 0, 3 multiplied by matrix row-wise first row x second row 4 third row 1 is equal to 0. Given that we have matrix row-wise first row x minus 5 minus 1 multiplied by matrix row-wise first row 1, 0, 2, second row 0, 2, 1, third row 2, 0, 3 multiplied by matrix row-wise first row x second row 4 third row 1 is equal to 0. It implies that matrix row-wise first row x plus 0 minus 2, 0 minus 10 plus 0, 2x minus 5 minus 3 multiplied by matrix row-wise first row x second row 4 third row 1 is equal to 0. Solving this, we get x square minus 48 is equal to 0. It implies x square is equal to 48. It implies x is equal to plus minus 4 square root 3. Example. Find the inverse of the given matrix. Row-wise, first row 2, 1, second row 4, 2. Let the given matrix be A. We know that A can also be written as AI. Therefore, row-wise first row 2, 1, second row 4, 2 is equal to row-wise first row 1, 0, second row 0, 1 into A. Applying R1 changes to R1 minus 1 by 2 of R2, we have matrix row-wise first row 0, 0, second row 4, 2 is equal to row-wise first row 1 minus 1 by 2, second row 0, 1 into A. In this equation, on left hand side, we can see all the zeros in the first row of the matrix. Therefore, A inverse does not exist. Did you know? A rectangular matrix does not possess inverse matrix since for products BA and AB to be defined and to be equal, it is necessary that matrices A and B should be square matrices of the same order. If B is the inverse of A, then A is also the inverse of B. Uniqueness of inverse. Inverse of a square matrix, if it exists, is unique. If A and B are invertible matrices of the same order, then inverse of AB is equal to inverse of B into inverse of A. Summary. Let us summarize what we have learnt. If A is equal to Aijm by n, then A dash or transpose of A is equal to Ajin by m. Transpose of matrix A is equal to matrix A. Transpose of K into matrix A is equal to K into transpose of matrix A. Transpose of matrix A plus B is equal to transpose of matrix A plus transpose of matrix B. Transpose of matrix AB is equal to transpose of matrix B into transpose of matrix A. A is a symmetric matrix if A dash is equal to A. A is a skew-symmetric matrix if A dash is equal to minus A. Any square matrix can be represented as the sum of a symmetric and a skew-symmetric matrix. Elementary operations of a matrix are as follows. If A and B are two square matrices such that AB is equal to BA is equal to I, then B is the inverse matrix of A and is denoted by A inverse, and A is the inverse of B. Inverse of a square matrix, if it exists, is unique.